Chapter 16, Quantum Rotation, Section 16.5, the uncertainty principle for the two-dimensional rotation. For the two-dimensional rotation of a two-particle rigid rotor with a constant radius r0, the angle operator theta and the angular momentum operator L do not commute. We can prove this angular momentum operator is simply negative IH bar delta over delta theta. We start from the Cartesian coordinates. When we apply L to an arbitrary function psi, it's equivalent to negative IH bar and then x delta over delta y minus y over delta x applied to psi. And x is written here, y is written here. This delta over delta y is equivalent to cosine theta r0 times delta over delta theta. This delta over delta x operator is equivalent to negative sine theta over r0 times delta over delta theta. We derived this in a previous section. Now x is r0 cosine theta, y is r0 sine theta. That's just the conversion from Cartesian to polar coordinates. And now we have the sum of these two. Cosine theta squared plus sine theta squared is 1. And therefore, when we apply the angular momentum operator to a function, we get negative IH bar delta psi over delta theta for the two-dimensional rotation. Now let's look at the commutator of the two operators, theta and L. So when we evaluate this, we need to apply the commutator to an arbitrary function f. The expression is theta LF minus L theta F. Alright, we just switch the orders of the two operations and take the difference. And L is negative IH bar d over d theta. Alright, so that's why I replace L with this operator. And again, this is the L operator. Alright, so we just need to evaluate this. Over here, this is straightforward. This is just the first derivative of f, or f prime. This one, we need to use the product rule. The result of this one is f plus theta times f prime. We clean up everything, we get IH bar times f. So this commutator of theta and L is equivalent to this operator. This is a very simple operator. It's IH bar. When you apply this operator to any function, it's equivalent to multiplying this function by IH bar. This is non-zero. That means the commutator of theta and L is non-zero. Theta and L do not commute. We cannot determine the exact value of theta and L at the same time. And we have this uncertainty principle similar to Heisenberg's uncertainty principle. Delta theta times delta L must be greater than or equal to 1/2 of H bar. In this expression, L denotes the magnitude of the angular momentum of the rotation, but not the quantum number. So over here, this L is in terms of H bar. Note that in quantum mechanics and quantum chemistry, we use the same letter L to denote the quantum number of the angular momentum, which is an integer, and also the magnitude of the angular momentum itself, which has a unit of joule times second. And also we know the magnitude of the angular momentum for a 2D rotation is LH bar. For 3D, it's the square root of L times L plus 1 times H bar. So this can be a little confusing. We have two different uses for this lowercase l. But later in quantum chemistry, we often say this H bar is one atomic unit of angular momentum. And in that case, L times H bar is equal to L in the atomic units. So at least at that point, we know why L can be used to denote both the quantum number and also the magnitude of angular momentum.